Hello and welcome back to AB1202 Statistics and Analysis Week 9 tutorial. Today we have one topic, but one big topic, and that is two population means tests. Tests, that means plural, many tests below it. So even though we have one topic in our agenda, it's quite a broad one. So let's dive in. In one population means our goal was to find mu, right? So there are two ways to find mu. One is through confidence interval. The other one is through one population hypothesis test. In two population means test, what we are interested in is more to compare mu1 and mu2. For example, mu1 could be the population mean GPA of NUS students. Mu2, population mean GPA of NTU students. Right? So the situation arises typically in again disputes, right, or arguments that NUS students do better than NTU students. When we say no, NTU students do better than NUS students, or maybe Ministry of Education is conducting an experiment, a check, an audit to see if the claim that NTU is as good as NUS, does that have any evidence of support, right? So one way is to, compare the GPA. But as we all know, GPA, average GPA, because NUS will have a database of all students' GPA, right? And then NTU will likewise as well. So it is possible to actually calculate the mean and then compute. But suppose we are just students arguing, or just teachers or professors having a statistical debate, right, on this topic. And so we will not have the ability to download the database or seek requests to the IT departments to do this, because you need authority, right, for proper official purposes. Now, so if we want to compare mu1 and mu2, then as you know, it will fluctuate from year to year. So some years NUS might be 4.35, and then NTU might be 4.32. And other years, NUS could be 4.33 and NTU could be 4.41. So they go up and down, up and down. Some years NUS are better than NTU by a little bit. So the question becomes, that little bit, can we treat that as statistical noise or not? Is it okay, right, to treat the second decimal place onwards, right, whether that is higher or lower than NTU, NUS doesn't matter, because they are just due to randomness. So can we do that? That's the question, right? If that's the case, then we say the population means are essentially the same. But maybe it is up to the first decimal place. That means some years NUS could be 4.1, NTU 4.3. But other years, NUS 4.4 and NTU 4.2. So some years go up and down, and the number itself goes up and down for the same university even. So then, where is a fair way, objective way to, grab hold of the randomness and then put them aside and say that, hey, you know what, it is really clear that NTU is better than NUS, for example, right? Of course, a statistical lesson given by NUS side might just give the other way around as their example. So we want to know, is mu1 greater than mu2, or mu1 less than mu2, or mu1 equal or not equal to mu2? That's all. All the time, we don't know the value of mu1, mu2 itself. Okay. As a contrast, the moment we know that mu2 equals to 4.5, right? Let's say that's very accurate, because somehow during a presentation speech, the chief information officer of NTU disclosed this. We have been very good in the past few latest years. Our students average, GPA reached 4.5. Okay, let's say that was disclosed. So once this population mean GPA was disclosed and becomes a constant, then we no longer have two population means tests. Understand? All right. Because then in that case, we only do not know the population mean GPA of NUS students. And in that case, it becomes a one population means test, something we have already done. Just refer back to the hypothesis testing video. Very easily done. Okay, so remember that all the time when we conduct two population means tests, the goal is just to compare the outcome. The goal is not to find the numbers, then do the subtracting. Okay, so that's the starting point. Now, at this point, to proceed, I will really caution you to follow the steps that I give you. All right. They are very simple, questions and two junctions, left or right, kind of diagnosis steps for you to do your two population means test correctly and quickly. The first time you get it right. Okay, otherwise you might be lost in the woods. And it's very important to ask the first question here. Don't change the order, right? So is it a PET test or not? Is it a PET test or not a PET test? What is a PET test? PET test, you can think of it as taking measurements, right? From taking random survey from students, one from NUS, let's say that's X1, and one from NTU. Okay. The first pair is one student from NUS, one student from NTU. So let me just say that because semester is long, we'll have to wait a long time, right, before we get the GPA. So in order to conduct the study, let's just say we give the students a 10-question math test. So the students will start doing and then score, right? So the number will be from 0 to 10. So we'll record 5 and 6. So if it's a PET test, you can think of it as the comparison or the subtraction, the minusing is done across the rows. 5 minus 6, because they are paired together. Yeah. The second pair, well, we can say something like 6 and 2. The third pair, 3 and 7. Don't worry, I'm not going to do this indefinitely, but just give it enough, enough variations, right, to see the differences. Okay, like this. So PET test, you can think of it as finding the difference across the rows, right? 5 minus 6. Okay. Why? Why do we do that? First of all, why do we pair the NUS student with the NTU student? What's so special about that? Now that is a good question from me. Well, what's so special about them is because the experimenter, this particular survey owner, has a reason to pair that. What's the reason? The reason typically has to be socially acceptable, all right, or financially there is a reason, all right. Procedure-wise, right, the environment-wise, there is a sense, there is reasonable causes, right? There is good consideration of the relationship between these two students that they should be paired together, and therefore we do the subtraction amongst these pair itself. So not pairing randomly. So if you randomly pick a student from NUS and you pair it, so-called, you call it pairing, but it's actually not. You pair it and say, buddy, take care of each other. Then that's wrong. That's not pairing. Okay, then what is a good example of pairing? Well, there are many. I'm just going to give one. So these two students, they are twins. Okay. And what's so special? Because my object of study, if I'm the survey owner, is to understand, right, to test whether, I claim that, I assert that twins perform similarly in their university studies. Now there's a social reason, right? There's a good consideration of the various facts, the environment, that twins look alike. They have the same habits, they like the same kind of activities, and things like that. So it makes sense to extend that suspicion into they likely or they should perform the same. So that's the claim. So I'm making the claim that twins perform the same in their university studies. Is that true or not? Right? So that's the claim. So when I pick twin sister A in NUS, I have to pair it with twin sister B, all right, twin sister A, the other twin sister A, twin sister 1 in the NTU, right? I cannot, I should not, I must not pair that sister with some other students. That is the reason why we pair. Now, why do we do that? Well, because when we pair, there is a sort of a noise cancellation effect. So that when we say, oh, your result, your claim, and because you claim eventually that, yes, it's true that twins perform the same. Let's say that's the statistical conclusion. And others might accuse you of, the fact that some students are having rich parents and some students don't have. That's why when you pick a student from NUS, that student might be richer, having richer parents, right? So have more tuition sessions, have better exposure to, highly qualified teachers, have better exposure to challenging exercises, etc. Right? So you can be exposed to those accusations. And then you say, well, because these students, they don't have richer families, so they have to work part-time, and so they perform poorer. Your study hasn't taken into account those, right? Now you can say, wait, I have paired tests. When I pair them, I am having this cancellation effect, because when you say different parents, no, they are siblings, right? So I'm doing twins some more. Twins means they are from the same family, right? So even if I'm not doing twins, they are siblings. Siblings come from the same family. So if their parents are rich, then they are rich. And so both siblings will be exposed to more opportunities, more sessions, more tuitions, more whatever. And so they will cancel out when I minus them off, right? So that the only effect is due to the fact that they are twins, right? And if due to DNA twins, one is significantly doing better than the other, I don't care which one, so long as there's a difference, then it will come out as saying, to that extent, saying that twins don't perform the same, right? Then that will be an interesting outcome. So I would trust my result. So you see, my results are more robust. It can withstand known, because I would also think that, hey, by doing the subtraction, I would be canceling out the family rich or poor effects, right? Or unknown factors. I only thought about family. I haven't thought about social circles, right? The mix of friends. And what if the criticism come in that form? What if criticism come in other forms that I haven't thought of, right? So by pairing them up, so that there's a reason to pair them, you would be able to cancel out, all right, what we in statistics call the confounding factors, the influencing factors that tend to make one sample perform higher or lower than the other. But when you pair and subtract them, those factors confound, confuse, or influence both samples simultaneously, right? So that there is less ability for suspicious readers to try to attack you on that end. Now, you are not 100% immune from any attack. It's just saying that if you can pair, you have a reason to pair them, and you choose not to, then you are going to withstand even more potential attacks. That's all I'm saying, right? So long story short is, if you can pair, you should, because pairing is going to give you a more robust outcome to be able to withstand accusation of the reliability of the conclusion, the statistical conclusion, more robustly. That means it's able to tolerate more accusations and still, stand tall and say my conclusion is still reliable. Whether the twins perform the same or not, that conclusion itself. I'm not saying that the twins will have the same performance. That's a conclusion, but is it reliable, right? So it is reliable either way. If the study says twins have the same performance, I have very good confidence that that is very, very reliable, because it has taken into account both, the family, the social circles, the parents, the financial ability, right, and so on. Okay, so with that, then we will have to look at what happens if it's paired. Now, if it is paired, first of all, let's just draw two little icons to indicate pairing using my twin example. So it is paired, right? What does paired mean in terms of calculations? It means that, first of all, your n is equal to n1 equals to n2. Remember, n is your sample size. So if you look at my little example here, I've actually done 8 measurements. 1, 2, 3, 4, 5, 6, 7, 8, right? But in terms of the participation in the calculations, when you're doing paired two population means test, is that you only have 4 sample sizes. Okay, and n will be equal to 4. After that, what happens? Very simple, right? So what we do is we will assume. Okay, we will assume that D, the population of difference, or the difference population, is normal. In other words, we do all the delta, we all do all the subtractions. 5 minus 6, 6 minus 2, and all that. Well, why don't we just do that? So x minus x1 minus x2, right? Number wise. Okay, so this is D equals to, which is made up of di equals to x1 item number I minus x2 item number I for every I. Right, so for all the items 1, 2, 3, 4, 1, 2, 3, 4, you subtract row wise. 5 minus 6, you get minus 1. 6 minus 2, you get 4. 3 minus 7, you get minus 4. 4 minus 5, you get minus 1. That's the kind of element by element subtraction. Yeah, element by element subtraction. So once you have done that, we will then be able to sort of find the sampling distribution of sample mean for D, right? Because we are going to do the sampling. And we are sampling 2 numbers in order to produce 1 number in D. And after that, and these are the samples coming out from D, because there will be a lot more twins. There'll be a lot more differences that we haven't captured, right? Because we only have time and permission and consent form from 4 pairs. So that would conclude our study, but that doesn't mean we have measured all possible twins when one twin studies in NUS, exactly when the other twin also studies in NTU, exactly when we are also just getting ready to start our experiments and collect data. So it'll be very tough, right? So we end up getting only 4 twins, four sets of numbers, and we get this. Yeah, and therefore D bar, so this is D, the population of difference. When we sample, we obtain D bar, and because we assume that the population of difference is normal, so D bar automatically is normal, and so we are quite okay, because when parent is already normal or assumed to be normal, then we are okay. Many things work automatically, right? Then what happens is that we typically, right, have no knowledge of sigma 1 and sigma 2 of the x1 and x2. We have no knowledge. So in that case, basically, it's like we also have no knowledge of sigma d. Hence, also no idea of sigma d, the population standard deviation of the parent difference population here, d. So when we sample, we create d bar, right? And we will have S of d, which is basically the calculating the standard deviation here for the sample of size 4. And once we do that, we will basically be performing use t. So basically we use t. Okay, so parent is normal. No idea of what's the population standard deviation, and kind of regardless of sample size now, right? Because if you go through the one population means test, you will see. So once we have this, we are ready to say that the formula is just using t equal to d bar minus mu zero. Mu zero is the hypothesized difference, mean difference, right? In many cases, it will be 0, but later on I'll talk more about this. But you can see that the format is pretty much the same as a one population means test, because it is. Okay, so this is basically the so-called Z formula, right? But applied to the T case. And SD is simply the sample standard deviation, and D bar is the sample average. And we can also do a quick calculation because the total is -1, right? And the D bar is going to be what is it? -2, sorry. So the total is -2. So D bar is -2 over 4 equals to -0.5. So that is our calculation, and it is this D bar that we are talking about. So this D bar is going to feed into here. Okay, and D bar is the average of DI, where DI equals to, as I mentioned earlier, x1 of I minus x2 of I, and so on. Well, if you're getting a little bit confused by the i's here, or the double subscripts, is actually trying to be clear that x1 is the samples from population capital X1, x2 is a sample from the population of capital X2, and the I is the ith column. So this is the ith column, ith row. Okay, so the ith row. And the SD is the sample standard deviation of DI. So you calculate the sample standard deviation of this set here, then plug it in, and basically the test statistic is out. Right. So when you have test statistic and you sketch the diagram for T, find the critical values, and then you can just continue from there. And T, of course, comes with degree of freedom. Let's not forget the degree of freedom is going to be n minus 1. Okay, that's easy enough because it's almost like a one population means test. Next, if it is not paired, then what should we do? Okay, so we have the unpaired case. So in unpaired case, let's say they all swing to a side and So not paired, they're facing away from each other. And N1 could be equals to or not equals to N2. Okay, that means it can be zigzag. The columns can be zigzag. We can find 4 people in NUS, but 6 people in NTU, right? Maybe because of proximity, we can find 12 people in NTU and 4 people in NUS. So it can be different. Okay, so but whether to pair or not is not because of your ability to find the samples. It has to be the other way around. First decide, right, whether it is pairable or not. There's reason for you to pair or not. There is association, there's relationship between the pairs or not. That means they come from the same source, they are influenced by the same factor. You know, the students are taught from, or they graduated from the same high school and primary school, okay, even though they are from different families, the students, not siblings anymore, but they were from the same, you know, primary and secondary schools. Okay, or in an international university, these students are paired because they're both from Singapore, right? And these are paired because they are from China. These are from India. So then you're doing sort of a pairwise study. That means regardless of which country they are from, is one doing better than the other? Okay, so if your objective is to see NTU is better or NUS is better, so that you can nullify the effects of different countries' primary and high school education success. Okay, so let's say they are better prepared, they are ill prepared, they come to a better university with ill prepared primary and high schools. Somehow they manage to get admitted in. They still do well or not do well, right? So if you want to remove that noise, right, the country of origin, then you might want to pair them for some reason. So again, this for some reason is sometimes very varied, very different from case to case, from study to study. So if there's a reason to pair, then you pair. And when you pair, the sample sizes must be the same. So when you do not pair, first of all, sample sizes may or may not be the same. All right, there's no requirement. Then we want to say that, are the variances known? Okay. Did we know them? Do we know their values? That is, right? So if yes, we know them as values, then what we do is we typically means in most cases you will also do that without having much harm, or without exposing yourself to accusations that that's not reasonable, that is not really true, you know, that kind of thing. So typically we will assume parents, assume that parents means x1 and x2 are normal. Okay, so that when we perform the subtractions, x1 minus x2, and therefore x1 bar minus x2 bar, the results will still be normal. The difference of the sampling distribution of sample means is going to be normal also. And you understand the beauty of being normal, right? Because being normal means we can run in R the Q norm, P norm, and in Excel we can run the norm.dist, norm.inverse, right, easily. So again, a lot of mathematics will be a lot of mathematics in statistics will be well supported if the population we are working on is normally distributed, right? So let's just also put a note. Okay, no worries. That's always nice to read. No worries. What's that? About sample sizes. Okay, because we already know the population standard deviations and variances. We know them. and we are assuming parents are normal. So basically, we are talking about two populations that are normally distributed, right? And you know the variances. That means you know the population pretty well, well enough to know the values of their individual variances, right? So in this case, what do you do? Well, not surprisingly, we're going to use Z distribution. Okay? So when we do Z distribution, our test statistic will look like x1 bar. So we sample x1, we bar it, we find the mean itself, don't care about x2. Then we minus x2 bar, same thing, we just look at x2 column itself. So it can be long or short, right? Irregardless of x1, and you just bar it. You just find the mean minus the hypothesized mean difference over the standard error of the difference of the sampling distribution of sample means. So that is basically going to be the sigma 1 square over n1 plus sigma 2 square over n2. Notice this is just the variance of the sampling distribution of sample mean for x1. This is the variance of the sampling distribution of sample means for x2. When x1 bar minus x2 bar happens, variance of x1 bar minus x2 bar, assuming they are independent, is just variance of x1 bar plus variance of x2 bar. Right? And then you take the square root to get the standard deviation so as to plug into the Z formula. So actually it's all following the basics that we already know about. Yeah. And why don't we also extend this little sampling activity, right, towards here. So we will write down x1, x2 quickly. And this time round, there is no need for labeling the first pair, second pair. So we have 5 and 6, 6 and 2, 3 and 7. More like each column is concerned with itself. So x1 is concerned with its own sampling, right? And then what we do is we will, let me just clear this part. Okay, we will just mean it. Right? So we will just calculate x1 bar, and x1 bar is going to be sum of all divided by 4, so 11 plus 8. 11 plus 7, so 18 divided by 4, and we get 4.5. Right. The other one, we do the bar on its own, we get x2 bar, and that is going to be 8 plus 12, so 20 divided by 4, 5. So we get 4.5 and 5. And in this case, the D bar is the subtraction of x1 bar and x2 bar. So that's 4.5 minus 5, we get minus 0.5. Now notice that this result minus 0.5 is the same as the earlier result, minus or negative 0.5. Okay, not sure if you can see, but I will just read it out. Okay, and this is not a coincidence, not because I purposely choose the numbers very carefully, but it will happen with any number when the same numbers are used in the paired and unpaired case. But of course, the moment you add some more numbers to x2, you change the sample sizes for both x1 and x2, the difference will be different. Okay, so first thing first is that at equal sample sizes, right, you can do paired or unpaired test. Numerically, you can just go ahead. But I'm saying don't randomly choose just because you can go ahead. You have to exercise this power very carefully. Consider whether the measurements, the entities, have any good reasons to be paired in order to make your outcome very solid, very reliable, very resistant to attacks, either by known factors or unknown factors to yourself at this point in time. Yeah, so you decide. So as a student now, when you perform or you try to find answers to these questions, don't decide whether you have you can or cannot perform these calculations. That means I try to minus and I don't, and I cannot. So that's why I use unpaired, right? But in the case of equal sample sizes, you can both. If you just look at the numbers, you can do either unpaired or paired test, right? And the result, the D bar, will be the same. This being the same is not implying that, oh, it doesn't matter whether you do unpaired or paired test. No, not true. Because remember, uh, this is a partial view of the entire universe, right? Right? And for the paired universe, that means the population of the difference itself, there will be exactly, capital N number of twins. There's no such thing as one sibling twin, right? Yeah, so it has to be always in pairs. Yeah, okay. So in that case, there'll be, that number. But in the case of unpaired calculations or measurements, the actual population can be that x1 is much larger than x2, or the other way around, right? And therefore, in the population mean of the difference here, that means mu of d bar is going to be different from the mu of this d bar, because it's pairwise subtractions. The actions are all different. The way you mince the meat is different, right? So in the bigger sense of the entire population, the values will be different, even though at the sample level, it seems like the same. So this is not the justification that pair and unpaired doesn't matter. They matter, right? They matter. I need to stress this because I've heard from even very experienced teachers trying to justify that it doesn't matter pair and unpaired. Look, see, this is a proof that it is the same. So numbers being the same, therefore the whole procedures, when actually one uses T, one uses Z, they are the same. That would be the collapse of the universe, right? No. Okay, so the other way around. Decide whether you should pair or not pair first, then come down this way, right? So following the chart. Yeah. So far so good. So up to here. Then again, you calculate that everything is there already. This again, I want to show the link, and this number goes towards this value here, right? So this is x1 bar minus x2 bar. Okay. Next, we want to talk about what happens if sigma 1 square, sigma 2 square, they are not known, right? Or one of them is not known. So in the case of, we actually have a good estimate of sigma 2 square, and that's 2.1. Sigma 1 square, that's NUS variance of GPA. We don't know, right? Because we have very little information. Then what should we do? Then we pretend both we do not know. Safer, more conservative, right? Because if you assume that NUS variance is the same as NTU, yeah, maybe there's justification because the students are about of the same age, about of the same intelligence upon admission, and so on. It's still a big assertion, isn't it? Because you really have no data. So then we will fall back as if we don't know both. Then what do? We ask sample sizes large, right? Large or not, obviously has got to do with the central limit theorem. And 1 and 2 both are larger than 30. Okay? If yes, then what happens? If yes, then of course, license to kill, right? License to assume normal. So yes, by CLT. Well, that's important enough. So we say by CLT. By CLT, x1 and x2 bar are normal. Here I bar them. This bar. This is the sampling distribution of sample mean. That means we sample x1 then we bar it, treat it on its own. Then we sample from X2, then we bar it. We treat it as if we just sample from X2 alone, right? And once we have them, we perform a subtraction. So that means these two are already normal. Okay. And so D bar, which is made up of X1 bar minus X2 bar. So it's a composite random variable. It is derived from the difference of the sampling distributions of sample means of population 1, then minus that of the population 2. Okay, so it's made up of this. So this is also normal. Because subtracting normal from another, if they are independent, if X1 and X2 bar, they are independent, is going to make the resulting distribution also normal. So we just do that. And what happens then? So we will then, so we use point estimates. That S1 bar, S1 square, sorry, point estimates sigma 1 square. S2 square, sample variance of population 2, point estimates population variance of population 2. And let's put a note that it is reliably, because remember, sample sizes are large. That's the beauty of hard work, right? So we did a lot of hard work, we touched reality a lot, we measured a lot, so that we have a good confidence to say, no, it's actually, the variances are actually very small. The other one is actually very large. We have that gut to say why, because we did a lot of hard work, right? So it is reliable, and we use Z, of course, because CLT always asks us to use Z. Okay, so we use that, and the resulting formula is going to be the same as what we see on the left. So X1 bar minus X2 bar bracket, that itself is the difference of the means, whereas earlier on is the mean of the difference, right? So D bar is the mean of the differences of the individual values. So we minus off the hypothesized value that is in the hypothesis. Then we, for the Z formula, we should be taking the square root of the variance sum of X1 bar and X2 bar. But if you trace upwards, we don't know sigma 1, sigma 2 square. So fortunately, we can use S1 square, S2 square to point estimates. That means treat them as if we knew sigma 1 square, sigma 2 square. Which is true, right? Because we checked that N1, N2, they are large. So that CLT guarantees us it's normal, and the point estimation is going to be reliable thanks to our hard work. So we will then substitute x1 square into sigma 1 square, s2 square into sigma 2 square, and then the whole calculation, even though it looks a little bit lengthy, you can just plug into R or Excel, and then out comes the number straight away, and then you plot the Google pin on your Z distribution and immediately decide whether to reject or not the null hypothesis. Okay, so far so good, and we are down to our last branch, which is now that we have N1 and N2 known to be small, okay, so they are not large, and this is also common because, for example, if you're doing COVID-19 test, right, and we expose the patient, the COVID-19 infected patient, who otherwise is healthy, but otherwise, he's infected with COVID-19, to two different medicine, new drugs, right, that claim that they can cure the COVID-19. So we're going to expose two different patients, one to drug A, one to drug B, and see which one is sort of the recovery is shorter, therefore better. So we can measure recovery time, we can measure blood samples, and then count the cells and whatnot, right? With that, we don't care. We just think that there is a medical procedure to measure the extent of how good is good, medically speaking, then we will need to find, first of all, COVID-19 infected people who have to satisfy certain stringent medical conditions. They haven't shown symptoms. They haven't taken any drugs, or they have already done n times of or 3 times or 6 times of vaccinations. Certain very stringent procedures, and all patients must qualify all these conditions before they are being put into a population or a sample. So you can understand the sample that we can receive will not be a lot, right? But then out there in the whole universe, on the whole earth, there may be a lot of such people, but we don't know them. They didn't know there is this clinical trial. They didn't know there's reward. Otherwise, they would have volunteered, and so on and so forth. So end up you only have 5 patients. So that's why typically in many cases, n will not be large, or n will not even reach 10, not to mention 30. So 30, even though it seems low, it is very hard to reach. How many developed countries are there? If you count, of course, there are different people who count differently. You also struggle to try to reach 30. Okay, if you go by GDP can go up and down, right, across different years. If you go by national debt can go up and down. If you go by GDP per capita, it can go up and down, So you also struggle to reach 30, right? So 30 is a small number mathematically, but in practice, it is a very tall ceiling. So in this branch, we need to ask another question. Can we assume variance to be the same or not? This is a rather important step, because many exams and test questions will really force you to look into this. Right? So we want to decide. There are some ways to decide equal variance, such as F-test. All right, so you can perform an F-test to decide if the sample variance of S1 square, right, is equal to S2 square or not, right? Sigma 1 square is equal to sigma 2 square or not. Or a quick check, which is of course subject to people's accusations. Can be, I just put example 0.5. Okay. So S1, take the sample standard deviation of sample 1, divide by sample 2. Now, why sample 1, sample 2? Which one is sample 1, which one is sample 2? Because if I swap them, left becomes right, right becomes left. So which one is sample 1, sample 2? Doesn't matter. Because this is a tight range. So if you say sample 1 is 1, sample 2 is let's put it back. Sample 1 is 2, sample 2 is 3. So 2 over 3, 2/3. That's here, right? Okay. But what if I do 3 divided by 2? Then it's 1.5. It is still okay. So it doesn't matter. Yeah. So you just use S1 over S2. So are the variances equal or not? That is sigma 1 square equal to sigma 2 square or not? If it is a yes, okay. If it is a yes, then we know that sigma 1 square is equal to sigma 2 square. Then what happens? Well, then we will use equal variance t-test. Okay. So use t. I just wanted to say use t. Where's my... Okay. Use t. Okay, so this is called the equal variance t-test. Or pooled variance t-test. How does the test statistic look like? Well, it looks like this, t, right? So we use t, so it's a t-test basically, and the numerator looks exactly the same because we are talking about the difference of the means. So this will be our input in the first place, right? Then less of the hypothesized difference, normally 0, right? But it can be different. And then we divide it by a pooled variance, let's say SP, right? So that's our variance, and we treat the SP as the variance for both x1 and x2. So SP square divided by n1 plus SP square divided by n2. The pooled variance is pooled because we assume that the parents x1 and x2 have the same variance. And we can assume because both variances are unknown. We don't know them, or we cannot know them, or it's very expensive to know them. So is it possible to assume that they are equal? Okay, like I mentioned before, can we assume NUS variance is the same as NTU's variance? If you and I, right, just maybe students talking, and we have no access to the NTU database, much less to talk about NUS database, so we have no way to calculate the actual population variance. Our only way is to guess. Can we assume that the two variances are the same? Then we go by a bit of external logic. So we say, well, look at the students. They're all about the same age, right? They are all pretty intelligent because they pass through various tests and checks before being admitted. So they are, like, roughly speaking, about the same intelligence. And so it should not be too much objection for us to assume that they are the same variance. This is the external logic kind. So you can, without using all the tests, right, like F-test and all the quick check and all these things, you can then make the assumption. If that is okay, then we proceed down and use t-test. And we assume that they are same. And what does that buy us? What advantage does that give us? Because assuming that sigma 1 square and sigma 2 square, two unknown pieces of information, are equal, is going to degrade the quality of our output. Because the more assumptions you make, the less reliable is your output. You assume this, assume that, right? Assume exam is easy, so I don't study. End up, you crashed, right? So you cannot assume this, assume that. It's better to make as few assumptions as possible. But if we make such a trade-off, we give in, we say, okay, let's make an assumption that they are equal. What benefits do we have? Remember this part? Now we come back to here and say, wait, our sample sizes are actually very few and very small. Like N1 is 5, N2 is 4. Okay, something like that. So very, very small. Therefore, individually, if we use sample 1, size 5, to point estimate the variance of population 1, it's going to be very unreliable. Okay, and it's unreliable all the way to 29, right? Same thing with 4 samples, 4 measurements from N2, from X2. We want to point estimate sigma 2 square, the population variance of X2. That's going to be very laughable, right? So what should we do? We combine them and say, wait, X1 and X2, they have equal variance. Okay, let's just say the secret is both variances are equal to 3, the same number. We're not saying that the variances are affected by the same factors, like the variances of GPA in NUS and variances of GPA in NTU, they are affected by the same factor. Maybe yes, but also there are differences, right? So we're not claiming about the factors, the causes and all that. We're just saying the number. All right, at this point in time, the variance of GPA of NTU and variance of GPA of NUS, even if they are different, it's very small. So let's say they are the same. So we make that assumption. There's a little bit of crack in our conclusion already, a bit unreliable, injection, the injection of unreliability has gone in. What benefit do we have? Now we can combine the samples. So if we say S1, the sample standard deviation of sample 1, and S2, the sample standard deviation of sample 2, each is estimating 3, the number 3, right? So why don't we combine them both? Which now gives us a total sample size of 9, like almost twice as large as individual alone, right? So when we combine, we get a much larger sample size. Maybe it hasn't exceeded 30, but we are better off having a sample size of 9 to estimate this variance 3 than to have a sample size of 4 or 5 to estimate this variance 3. So you get the idea. And the trick is to combine the samples to give a common variance SP. Another way to talk about common variance is the pooled variance. So the way to calculate, so the way to calculate SP is none other than just using SP squared, okay, is first get back the squared differences. So for sample variance from population 1, you will add up all the squared differences, then divide by n1 minus 1. So now we multiply back. So we get all the sum of squared differences from S1. And then we do the same for S2. So that the numerator here will be sum of squared differences from all the sample entities. And then we divide by something like n1 minus 1 plus n2 minus 1. So that's going to be n1 plus n2 minus 2. That makes sense, right? It's like a weighted sum. If sample 2 sample size is a lot larger, like 16, and sample 1, the sample size is 4, then the pooled variance, the combined variance, should listen more to sample 2. That would make more sense. Yeah. So that is the whole point. Okay. So with this calculation of common variance or pooled variance, then we are done. All right. So this is actually the pooled variance. And is used to point estimate sigma squared, the number that is supposed to be the same as sigma 1 square and sigma 2 square. You see that? Yeah. So that we can then very comfortably plug it back in and think that as if we know sigma 1 square. So sigma 1 square is O, the number is just SP square. Sigma 2 square, O, the number is just SP square. Same number, right? So that's it, right? Very, very simple idea. And if we cannot, so if we cannot, what happens if there is a strong logic, there's a strong reasoning, there's a strong understanding, there's a supplementary note or whatever it is, right? That says, no, you cannot use equivariance. Maybe in the test or exam, there's an extra sentence saying that variance equality tests on the 2 samples have failed. That means they are not equal. It's known to be not equal, or it's known to be statistically not equal, right? So then, generally, sigma 1 square, sigma 2 square not equal, and they can be very unequal, right? So sigma 2 square is 10, sigma 1 square is 2 or 1, right? So they are very unequal. Then in this case, what happens? Well, we will use T, right? But what is known as the Welsh test or the Welsh Satterthwaite t-test. In a semester when I was a little bit bored, I forcibly asked a student, can you please pronounce this name? And You at least have to pronounce it right. So instead of saying Welsh Satterthwaite t-test, the student, of course, I call him by name, and maybe he panicked. He said, "Oh, Welsh Satterthwaite t-test." Okay, fine. So I mean, I shouldn't be laughing at his pronunciation, but it was good entertainment, and that I keep remembering all the time. Satterthwaite. Anyway, so Welsh Satterthwaite t-test. We better pay due credit to these people who created this very, very interesting idea, right? What's this idea? This idea is t-test, but with adjusted degree of freedom. Oh, that means I should add the degree of freedom here, yeah? So the degree of freedom is just n1 plus n2 minus 2 is df. Notice how this looks like the denominator in the pool variance, yeah? So very much related. Okay. So what is this Welsh t-test? Very simple. We are supposed to use t-test. We just need to know what is the test statistic. Not surprisingly, the numerator is going to start with x1 bar minus x2 bar, yeah? Because that is the fundamental ingredient, like it's like the DNA flowing through. Whether you use T or Z, you are testing the differences of the means, right? So that's why. Then you minus the mu 0 over, and because we do know they are different, so what we do is we will use the variances of the sample variance as literally the point estimates of the population variances of x1 and x2 respectively. Okay. Now, of course, you remember that we were saying, hey, you know what? Because n1, n2, they are not large, right? They are not large. They are 4 and 5. They are 6 and 9. Okay, they are not large. Then how can we still do this, right? That's the intellectual contribution by Welsh and Satterthwaite. The idea is we can do this, right? Knowing that there is higher uncertainty in S1, S2, given that N1, N2, they are small, so they don't qualify for CLT, then the Welsh t-test says we can adjust the degree of freedom. No need to calculate pool variance, but you want to not use the standard N1 plus N2 minus 2. Because N1 plus N2 minus 2 will be concrete contribution from N1 samples, right? Then concrete measurements from N2 samples. They are small, but when you combine, that's a bit larger, like about twice as large. And so given the pool variance, everything will work out, right? So that would be the pool variance way to accommodate for the uncertainty. But there's a trade-off. We have to assume the variances are equal. But if this trade-off cannot be made, and we still have small sample sizes, and the variances of small sample sizes are also still known to be unreliable, then the only way is to adjust the context, is to make the t distribution a little bit fatter, right, or a little bit thinner, so that the tails at the far end, will be adjusted correctly to reflect the fact that S1 square is actually a poor estimate of sigma 1 square. S2 square, poor estimate of sigma 2 square. That's the basic idea, basic thinking. Adjust how? How do you do the adjustment so as to be right mathematically? This is again the detailed technical contribution from Welsh and Satterthwaite. Right? So what they say is this: you add up the standard error squared, right? The variance from the sampling distribution of sample mean from x1 and x2. Then you square it some more, right? And then you divide by same thing, S1 square over N1, right? So that you just make a copy of this, then square it times 1 over N1 minus 1. That means the degree of freedom for X1. Plus, again, the same, because it has to be symmetrical, S1 and S2, right? They really have no sort of leftness or rightness. Huh? So you have to treat, the whole formula should be symmetrical about S1 and S2. So N2 minus 1, that's all. Okay, so this degree of freedom is to change the shape of the T curve, right? Make it reflective of more uncertainty. More uncertainty is as if we had done some additional measurements, as if our sample sizes were larger. So if we have, sorry, that's more reliability, right? If we have done more sample sizes, then our knowledge about the reality will be better. And so there's less uncertainty. So this is the highest degree of freedom we can get by doing N1, example 5, and N2, example 7. If we do 5 measurements and 7 measurements, then 12 minus 2, 10. Degree of freedom 10 is the highest degree of freedom. Higher degree of freedom reflects more understanding of the reality, less uncertainty. Yeah? So when we do this, the resulting number has to be lesser than N1 plus N2 minus 2, no matter what is N1 and N2. So if we were using the previous example, N1 is 5, N2 is 7, then this number, this degree of freedom, will be lesser than 10. And even fractional. So the answer could be, I haven't done the calculation because it depends on all the numbers here, but the answer could be 7.23. Okay, the answer could be 5.95. So there's a big discount. So it's as if, even though you have done 12 measurements, N1, 5, N2, 7, you have done 12 surveys. The effort is a lot, right? 12 units of effort. The Welsh adjustment of the DF says, no, because the effort is not big enough, you should treat it as if your effort is 5.9 only. And that makes sense, right? It's as if if you want to point estimate separately, or because the variances are different, you use each to point estimate separately. And so the knowledge about the variance of population one is very little, right? Only 5 measurements, and the other one 7 measurements, only 7 measurements. So finally, the knowledge of T value itself is a huge discount. It's not the sum of 2 minus 2, the sum of N1 plus N2, then minus 2. No, this is the highest degree of freedom. What you have is, after this adjustment, your efforts, right, given that sigma 1 square and sigma 2 square, they are highly different, then it's as if your effort is only 5.9, as if your effort is only 6.3. Right? And fractional degree of freedom is acceptable because T distribution is basically completely artificially constructed. So it is definitely okay to have fractional degree of freedom. Try it with your Excel or your R, and you will find that there's no problem at all, no error, nothing. Okay, next. We want to talk about quickly the last part of it. How do we form the hypothesis? Okay. So we start with a claim, right? Okay, we start with a claim, and the claim says that NUS mean GPA is higher than NTU mean GPA. So there's this claim. Or NUS is not much higher than NTU GPA. Or NUS GPA is the same. Basically, both our schools are good. So when people try to be politically neutral, actually, why are you arguing? Both schools GPA, they are good. Is there basis for saying that, right? Is there basis for saying they're equal? They're both good, right? So that's always, again, same as one population mean hypothesis testing. Why we do this is commonly, coming up from arguments, debates, investigations, planning, because we are planning for the future, right? And if the school is not doing well, maybe it's due to funding, we should give them more funding. And doing well or not doing well, one measurement is perhaps the student's GPA, right? The average GPA. So whatever it is the case, we start with these claims. And of course, these claims need not be just the value itself is bigger or smaller. It can also be NUS GPA is larger than NTU GPA by at least 0.5 or more. So better in the sense of not just larger, right, but larger by a certain dictated gap that we state up front without proof. Also by at least this much. Yeah, that would very much enhance the ability of our two population means test, right? Because it's no longer just higher or lower. It can be the claims or the arguments can be higher by at least this much, right? You owe me money so many times. Your amount of owing me is always by at least 1,000 or more, right? So something like that. So that is extending the territory of writing the claims. So I'm just giving some arbitrary numbers. Yeah. So the claim is like that. And what we want to do is to put that down in words, right? So into a statistical communication form. And so the standard way is H0, H1. So the claim goes to H1 because it is inequality. So mu1 minus mu2 greater than 0. Or you can substitute the 0.5 right here on the right-hand side. Very easy. That's why I say if there is a stated difference gap, it's stated upfront, then you just put it on the right side. Instead of 0, you just put the 0.5. If it is as it is, mu1 greater than mu2, then when you bring mu2 over, you get 0. So this 0 is important. It's not a sort of eyesore. So some students find it a bit of an eyesore and try to get rid of it by writing mu1 greater than mu2. Actually, it's less good because this 0 is it's like a parking lot. Now you park 0. But then if the claim or the arguments or the dispute added in this assertion that, wow, mu1 is greater than mu2 by at least this much, right, by 0.5, then how do you put the 0.5 in? Then that is very easy. Just replace the 0 by 0.5. Okay, next alternative is some students will change this into mu2 minus mu1. They just like to somehow say mu2 minus mu1, 0 is greater than mu2 minus mu1. First of all, never put the constant on the left side. Okay, so always do the put the constant on the right side. That's the convention. That's the way many textbooks will print this hypothesis. That's the way you will see when you Google search for examples and solutions and pointers given by other people. So always put the constant on the right side. On the left side, don't try to confuse yourself. The only advantage, if at all, of writing mu2 minus mu1, right, is really nothing much. Really nothing much. Because maybe you just want to show the teacher that, hey, this is greater, but then I changed to less than. Because when you move this over, you have to write mu2 minus mu1 less than 0. So this part becomes less than 0. Okay, so that's no good because first you are having a claim of greater, but you write down less than. That's bad, confusing. And number 2, you write mu2 minus mu1. It's in an out of order fashion, right? So why would you want to confuse yourself? Furthermore, it's during exam or test, right? So don't do that. Always, that's why at the start of this video, I already said, stick to 1-2 sequence and don't change to mu A minus mu W greater than 0 because some students like to contextualize it, right? So if university A and university W, then they say mu A and mu W. For me, I would rather just say, let mu1 be the GPA of University A, mu2 be the GPA of population mean GPA of University W. Then I come back to my notes, which is always writing in 1 and 2, right? So since I've already defined 1 and 2, I can just follow through all the things, all my notes in a 1-to-1-2 fashion. So it'll be very clear, very copyable, very downloadable, very readily usable knowledge here. Okay, so stick to this form. Okay, then we have mu1 minus mu2 the other way around, and it will be pretty consistent, right? Because the claim is greater and the complement is less than equal to. And same thing, if it is 0.5, then you put also, instead of 0, you put 0.5. Okay, and what about this? Not much of a surprise. You will say mu1 minus mu2 less than 0. Yeah, mu1 minus mu2 greater equal to 0. So again, if it is by at least -1, then you just put -1 instead of 0 here. So far, so good. And I suppose you can guess how to write the third one. And the third one is equality. And this is the exception, right? So the exception is going to go into H0. So we have mu1 minus mu2 equal to 0, or if it is saying that by 6 points, exactly 6 points, then you put a 6 on the right side. And H1, mu1 minus mu2 not equal to 0, or plus 6. And that's covering all the possibilities already. But this is for unpaired case. So please take note. And reason why I started off with unpaired case here is that it's just more natural, right? When we say, is mu1, the population mean of NUS, is it larger than population mean of NTU, right? So it's just very natural to think about that. And that situation will give rise to unpaired test, because you will randomly sample students. In fact, you don't want to purposely zero in on twins, one studying in NTU, one studying in NUS. It will be counterproductive, not helpful to your original goal of verifying whether one university is performing better than the other university, right? So in this case, you really want to randomly select students. So it's definitely an unpaired test. But if your purpose of study starts off with the statement that, do twins perform the same in university studies, right? Then that's a different story, right? So then you want to start off with a paired kind of statement. And paired statements will be more like, I should say, is the population mean of the differences, right? So mu D is the population mean of the D, the capital D, right? This D, of the difference population, right? Is it greater than 0 or by 3 marks, right? Or mu D is less than 0 by -5 points, or mu D is equal to 0 or by +2. And by now you understand the by, right? So if the claim has added in these numbers, the person says, I think the difference is at least 3 points or more. So the person asserts the 3. The 3 came out from the person's mouth, right? The 3 came out from the statement without proof, right? Then you want to put that 3 in, because it's not just greater than 0, it's greater than by 3 or more, right? Okay, so in this case, we would translate them accordingly into, this is like a one population means test. So actually no big surprise here, that we will put the claim into H1 and H0 will be the other way around. Yeah, and this will put the claim into H1 as well. Mu D is less than 0, H0 mu d is greater or equal to 0. And finally, this is equality test. So we put it into H0 itself. Mu d equals to 0. H1 is mu d not equal to 0. Okay, so obviously we will do a plus 3 and plus 3, right? Plus minus 5 to replace the 0 if minus 5 was mentioned, and plus 2 to replace the 0 if it was mentioned. So again, now this set will be the kind of hypothesis you use for PET test. So please don't mix them up. I've seen students knowing that they want to do unpaired tests already because they do know that, somehow by feel, right? They already saw the test question saying something like, you may assume equal variance. Equal variance only happens in the unpaired world, right? It never happens in the paired world. So they already intuitively knew that they have to do an unpaired test. Then what happens? Then what happens was that they simply write this mu d less than 0, right? Something like that. So this would be a bit weird because the hypothesis doesn't match the test statistic. So of course the student will lose marks along the way. So please don't do that. If you are a student studying through this video, you at least now have been told the obvious wrong methods that most students have done before you. Okay, so we've gone through a lot here, but I hope this whole world map of everything that you need to think, do, and write, actually more than that, right? Plus some sample calculations as well, in your tests, exercises, or exams have already been presented in a single piece of paper. Quite an amazing feat, I would say. All right. And I think I better shift to the right a little bit in case my very big image had earlier on covered the writings. Okay, so they are then shown here again. Upstairs here, just writing out the claims, and I'm sure if you've seen one, you know how to write the others. Of course, I've gone through some leeways that you shouldn't be exploiting, right? So like swapping mu1, mu2, like swapping the signs and all that. Don't try to do that, right? Don't change the 1 and 2 to other letters or whatever. Keep them as is because already it's complex enough, right? So you want to keep things as standardized as possible. And over at the bottom, in case I accidentally covered some of the formulas or the writings, I just want to have a good image of that again here so that at least you can screen grab if necessary. Okay, that's all I have. And thank you so much for your attention for this video session. I'll see you in the next session. Thank you and see you. Bye.